in section 11.3 is on something called the number e. E is like pi. It's not a variable. It's an irrational number. And we're going to discover here where the number e comes from, and you're actually going to find out what numerical value it holds. 1 plus 1 over n to the n is an expression that represents the number e. So when you plug in 1 for n, 1 plus 1 over 1 to the first power is going to give you 2. When you plug in 5 for n, you're going to get 2.48832. When you plug in 10 for n, you get 2.59374246. I'm basically writing all the digits that show up on my calculator. When you plug in 100, you get 2.704813829. When you plug in 1,000, you get 2.71692392. I want you to notice that the digit in the tens place has now kind of leveled off, so we know it's going to be 2.7 something. When we plug in 10,000, we get 2.718145927. 100,000, we get 2.718268237. And then we're going to plug in 1 million and get 2.718280469. Now we could keep plugging in larger values for n, but you can kind of see that this is the beginnings of this constant e that we're going to use in exponential and logarithmic functions. There is a function on your calculator for calling up e. E is the second function above the division sign. So if you see the division button, you'll see a little e there. And if you hit second division sign, you'll see it pops up with, I'm going to go back and hit the right buttons. It pops up with 2.718281828 ... And that's where we were going as we plugged in larger and larger numbers for n. I want you to notice on your calculator there's actually another place where you can find e. Second division sign is just the number e. If you press second and then the button that says ln, you'll see a little e to the x above it. And when you call that up in your calculator, it's going to call up e. And then if you have the new operating system, it's going to have a blank here, and you're going to fill in a number or a letter. If you don't have the new operating system, this is going to pop up, in which case your exponent would go here, and you would close the parentheses. What I want to look at real quickly is the graph of y equals e to the x. I want you to notice how similar it is to the graph of y equals 2 to the x. That's because it's an exponential growth equation, so the graph goes up from left to right, and all the same transformations for any other exponential functions would hold true for this. If you graph y equals e to the x plus 3, the graph would go up 3. If you did y equals e to the x minus 1, the graph would move to the right 1. If you graphed y equals negative e to the x, it would reflect the graph over the x-axis. If you did the graph of y equals 2e to the x, it would stretch vertically by a factor of 2. We're going to work with another exponential growth and decay equation, slightly different from the one we just used. This one, n equals n naught e raised to the kt. N naught is still your initial amount, your starting value. But this time we're going to use the exponential number e and raise it to the kt, where t is still time. K is really just, it's like r, it's your rate, except they call it k in this equation. When k is positive, it's a growth equation. If k is negative, it's decay. They're not always going to tell you k is negative outside of telling you that some value is decaying or depreciating or going down in value. in which case you'll need to know to plug in a negative for K. So in this first example, which refers us to some physics, according to Newton, a beaker of liquid cools exponentially when removed from a source of heat. Assume that the initial temperature, we'll call it Ti, is 90 degrees Fahrenheit and that K is 0.275. Write a function to model the rate at which the liquid cools. So remember, here was the equation we were just given. This is your initial amount. Well, T sub I is your initial temperature. So we're going to plug our temperature, we'll call it temperature final, is going to be our initial temperature, E to the KT. So all I did was I changed those N's to T's because our input and output are going to be temperature. Since the liquid is cooling, should K be positive or negative? Well, negative because it's decaying, it's going down in value. So our final temperature is going to be 90 E to the negative 0.275 little t. Now, in part B, it says find the temperature of the liquid after 4 minutes. Now remember, capital T in physics was temperature, little t was time. Don't get those mixed up or you'll mess up the problem. So we're going to plug in 4 for little t. And then we're just going to shove this in our calculator. Remember I said that e to the x is second and then ln, which is on the left-hand side of your calculator. And the calculator spits out approximately 30 degrees. And remember that's 30 degrees Fahrenheit because the initial temperature was 90 degrees Fahrenheit. Then it wants us to graph the function and use the graph to verify the answer to part B. So here's the graph, and I changed the window settings because the temperature was started at 90 degrees. Remember, the axes, this is going to be time and this is going to be temperature. And if you don't know that, then you might mix up the problem. So now that we know what the axes are, what I did was I changed the window to go from x minimum of 0 to x maximum of 50, and the y minimum of 0 to y maximum of 50. You probably could have used an x and y maximum of 40, but it really doesn't matter. We at least can see that the graph is going down from left to right. Now, in order to verify the answer to part B, I'm going to tell you about a different function on the calculator that you may not have used. When you go to second trace, you know, the place where intersect and maximum and minimum are, the first option was something called value. By the way, just to make sure you know, this is what I graphed in my calculator. I didn't write it in with the 4. If I had done that, then it would have just showed me that that there was a horizontal line, and you wouldn't have seen the horizontal line on the screen, so you would have had to search for it, but if you didn't know where to look for it, it could have taken a while. So instead, I graphed the equation we came up with in part A, and then what I'm going to do is I'm going to go to second trace and hit number 1 value. When you do that, at the bottom of the screen it says x equals. Since we want to know what the value is when x equals 4, if you type in 4 and then hit enter, it will tell you the 29.958, which is approximately 30. There's also a money equation involving E. This is the continuous compounding interest equation. It's a little different from the other compounding equation. The other equation, A equals P1 plus R over N to the NT, is for all other compounding of interest except for continuous. So the kicker is, on the test, if you see the word continuous, you'll need to use this equation. If it says annually, semi-annually, quarterly, monthly, daily, you'll have to use this equation. And we'll give them to you on the test. You're just going to need to know when to use them. So I like to call this the PERT equation because it looks like it's spelled out the word PERT. P is still your principal. It's the amount of money you put in the account. R is still your rate, and T is still your time. Remember that, compounding interest, we're gaining money. So R is going to be positive. So in problem number 2, it says, compare the balance after 30 years of a $15,000 investment earning 12% interest compounded continuously to the same investment being compounded quarterly. So I'm going to basically make 2 columns here. Let's do continuous here. U-us, nope, I can't spell. U-us, and this is going to be quarterly. Remember I said they're 2 different equations. Only continuous uses the PERT equation. So let's start with that. I'm going to put in $15,000. The rate's 12%, so it's going to be 0.12. And then we're putting it in for 30 years, so times 30. Remember, if you have the old operating system, when you hit second ln, this pops up, so you need to put in 0.12 times 30, then close the parentheses when you plug this into your calculator. And the calculator spits out $548,973.52. Be careful with money problems again. I've mentioned it before. If you have a problem involving money, you should always round it to the nearest hundredths place or to the nearest penny. Only if you're dealing in population should you round to the nearest integer, because you can't have 2.5 people in a house. You can have 2 people or 3 people, but not 2.5. All right, now we're going to do this again, but we're going to compound it quarterly. A equals P1 plus R over N to the NT. Quarterly tells me that N is 4. So we're going to do 15,000. 1 plus 0.12 over 4 raised to the 4 times 30. When I go plug this in my calculator, I'm just going to change that to 120 and not put in 4 times 30. It is better when using this compounding interest equation if you multiply N and T together before you put it in your calculator, because if you don't, a lot of times people think the calculator knows what it's talking about and they end up with an incorrect answer. So the amount of money I'm going to end up here if I compound quarterly is $520,664.81. Notice that I did not get the same amount of money at the end of my 30 years. Clearly, continuous compounding is better than quarterly. However, as I mention every year, please find me an account at a bank that compounds interest continuously, because if you can find one, I would like to put my money there, because they really just don't exist. When we get savings accounts or interest-bearing checking accounts, they only ever give you interest quarterly, 4 times a year. That's how it always works. Are there continuously compounding accounts? Probably out there somewhere, but I don't think they're for the general populace. And that was the number E.